The most dangerous part of this object is not where you think it is. Not the point where nothing, not even light, can escape. In fact, if this black hole existed on its own, crossing that invisible boundary might not even feel unusual, because you would never make it that far. Long before you could even reach the black hole itself, you would enter a storm of superheated gas, lethal radiation, and matter falling inward with so much energy that it shines brighter than an entire galaxy. This is TON 618, one of the most massive black holes ever discovered. And that's exactly what makes it so terrifying. Its enormous size changes the rules you expect. The closer scientists looked, the stranger the story became. How can the largest black holes have the gentlest event horizons? Why did the universe build something this enormous so early in its history? And why is the quietest part of TON 618 the one you would never survive to reach? Most videos about TON 618 begin with one number, around 66 billion times the mass of the Sun. It's an astonishing figure, but it hides the more interesting story. We have never photographed the black hole itself. We have never seen its host galaxy clearly. We infer its mass from light emitted by gas far beyond the event horizon, light that began traveling toward us when the universe was only a few billion years old. So this is not simply a story about a giant black hole. It is the story of how something this large can be both easier to cross and impossible to approach. In 1957, astronomers Braulio Iriarte and Enrique Chavira catalogued a faint object in a sky survey at the Tonantzintla Observatory in Mexico. It looked like a blue-violet star. They called it Entry 618. At the time, that was all it was, a faint point of light on a photographic plate. Quasars had not yet been properly identified as a class of object. The word itself did not exist in the way astronomers use it now. 13 years later, a radio survey detected strong radio emission from the same point. Follow-up spectroscopy showed a huge redshift. The light had been stretched by the expansion of the universe during an extraordinary journey. The redshift is 2.219. That means the light reaching us from TON 618 has traveled for roughly 10.8 billion years. We are not seeing it now. We are seeing it as it was when the universe was about 3 billion years old. At that early stage, galaxies were still assembling at a furious rate. Stars were forming more often, gas was more abundant. The universe was younger, denser, and much less settled than the one around us today. And in the middle of that young universe sat a black hole already carrying a mass commonly estimated at around 66 billion suns. TON 618 is technically a quasar. A quasar is not the black hole itself. It is the blaze created by material falling toward one. Gas and dust do not drop straight in. They orbit, collide, heat up, release enormous amounts of energy. The glowing disk can become so bright that it outshines the entire galaxy around it. NASA describes quasars as some of the brightest objects in the universe because the material around a feeding supermassive black hole can release more light than a galaxy containing hundreds of billions of stars. Around TON 618, gas farther from the disk produces broad spectral lines, fingerprints in the light. Astronomers study how wide those lines are. Wide lines mean gas moving extremely fast. Fast-moving gas means a powerful gravitational pull is holding it in orbit. From the gas speed, luminosity, and estimated size of the broad line region, researchers can infer the black hole's mass. That is where the 66 billion suns figure comes from. It is a serious scientific method. It is not a direct measurement. You might assume the most famous black hole in the universe has been precisely weighed. It hasn't. Virial mass estimates depend on assumptions about the structure and orientation of gas we cannot resolve directly from here. The number is best understood as an informed estimate, not a number carved into nature. The mass is enormous. The precision is not. That uncertainty is not a weakness in the story. It is the story. Here is the strange part. A black hole's event horizon gets larger as its mass increases. For the common estimate of around 66 billion solar masses, Ton 618's Schwarzschild radius, the radius of its event horizon, assuming a non-spinning black hole, works out to roughly 1,300 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. Neptune orbits at about 30 astronomical units, so using that estimate, Ton 618's event horizon would extend more than 40 times farther than Neptune's orbit. Not its accretion disk, not its glow, the boundary itself. Imagine standing on a spacecraft at Neptune's orbit. The Sun would be behind you, tiny and distant. In front of you, the event horizon would still be far beyond the edge of the solar system you know, and it would keep expanding around you for hundreds more Earth-Sun distances. That is scale. But size changes something else. The tidal force at the event horizon of a supermassive black hole is weaker than at the horizon of a small stellar mass black hole. NASA explains that smaller black holes can tear apart approaching objects before they reach the event horizon because the difference in gravity from one side of an object to the other becomes extreme. For a much larger black hole, that difference is gentler at the horizon. The larger the black hole, the quieter its horizon can be. If Ton 618 were isolated and inactive, an impossible thought experiment, but a useful one, crossing its event horizon would not be the instant spaghettification scene most films teach you to expect. The horizon would be almost anticlimactic. The universe would still be perfectly normal in your immediate surroundings, for a while. So why call it terrifying at all? Because Ton 618 is not an isolated black hole. It is an active quasar. The quiet horizon is buried behind a feeding environment powerful enough to erase any meaningful distinction between near and too near. As gas spirals inward, friction, compression, and gravity heat it until it radiates intensely across the electromagnetic spectrum. Quasars can produce visible light, ultraviolet radiation, X-rays, and powerful outflows. The black hole does not shine. The material failing to escape it does. You would not approach Ton 618 like a spacecraft approaching a dark sphere. You would first encounter an environment where radiation, magnetic fields, and energetic particles had already made survival irrelevant. Then the disk. Then the inner disk, where gas moves at a substantial fraction of light speed. Only after all of that would the event horizon matter. The least violent part of the journey may be the very last boundary. You would never reach the quiet part. That is what makes the title's claim defensible. Not that Ton 618 has uniquely malicious gravity. Gravity is indifferent. Not that it is certainly the largest black hole in existence. It may not be. It is terrifying because its size changes the rules you expected, while its quasar environment makes those new rules useless to anything trying to get close. The horizon is gentle. Everything before it is not. The final problem is not how dangerous Ton 618 would be if you visited it. It is how it became this large at all. The light we see left when the universe was around 3 billion years old. By then, this object had already grown into one of the most massive black holes known. Astronomers have several possible explanations. One is direct collapse. Enormous early clouds of gas may have collapsed into massive black hole seeds without first becoming ordinary stars. Another is sustained rapid accretion, where a black hole feeds efficiently for a very long time. A third involves mergers, smaller black holes combining repeatedly as their host galaxies collide. All are plausible. None is confirmed as the full explanation for Ton 618. Ton 618 is not frightening because it is impossible. It is frightening because it happened. The universe found a way to build it before it had much time to do so, and we are still working out how. A faint blue object on a photograph became a quasar. The quasar became evidence for a black hole of staggering mass. That mass became a scale comparison large enough to swallow the planetary map in your head. But the most useful thing ton 618 gives us is not a bigger number. It gives us a correction. We do not see black holes. We see their effects. We do not measure them like objects on a scale. We reconstruct them from light, motion, distance, and models. And when the model says a black hole existed this early, this bright, and this large, the right reaction is not to make the number louder. It is to ask what the universe knew about growth that we still do not. That faint violet dot from 1957 never looked dangerous. It was already one of the brightest engines in the young universe. The horizon may be quiet. The question it leaves behind is not. The universe has more stories to tell. See you in the next one.